Hello everyone. In the today's session, we are going to discuss some of the problems related to the operating characteristics of the DC series motor. So first problem is in this way, that is the torque armature current characteristics of a series traction motor are given as. So here they have tabulated some of the reading, that is for different armature current they have measured the torque. Hence they have tabulated the reading like this. So for this tabulation, the motor resistance is 0.3 ohm. If the motor is connected across the 230 volt DC supply, that is the speed armature current characteristics. So here they have told you that they have given the armature current and the torque tabulation, that is the torque reading they have given. But we have to calculate the speed armature current characteristics, and also we have to plot the speed armature current characteristics. First, let us list out the data. That is, voltage is nothing but 230 volts, and the resistance of motor is nothing but armature resistance plus armature series resistance. Because in the series motor, what happened? The armature winding will be connected to the series winding. Hence, the total motor resistance will be equals to the sum of armature resistance plus series resistance. But the series resistance is very small. Hence, we can also write the motor resistance as the armature resistance only. Hence, RM is nothing but RA. RM is nothing but RA, which is nothing but 0.3 ohm. And you can see here, we have calculated, that is, we have made a table to calculate this. So this will be very helpful. Hence, draw the table only to calculate the values. So here IA in ampere, so that is the armature current in ampere. They have already mentioned in the problem. Just write as it is, and the torque also they have given. So write as it is. Next, we have to calculate the back EMF. So back EMF formula is nothing but V minus IA into RA. Why we have to calculate back EMF? Because we know what is the armature current, but we have to calculate speed. So what is the formula for speed? Which is nothing but 9.55 into V minus IA RA into IA by T. Whereas V minus IA into RA is nothing but back EMF. Let us calculate this EB, that is V minus IA into RA. So here we know that V is nothing but 230 volts, and the armature current IA is nothing but 5 ampere, and the motor resistance is nothing but or armature resistance is nothing but 0.3 ohm. So substitute, we'll get the value 228.5. In the same way, for the second reading, substitute IA as 10 ampere, and again the V is 230 volt and RA is 0.3 ohm. So if you substitute, you'll get the value 227. Like this, we have to maintain V and RA value constant, and we have to keep on changing the IA value. So next, coming to the speed value, coming to the speed formula, again we have already calculated V minus IA RA, and torque also we have, and IA also we have. Now let us vary the IA and T value only. For the first calculation, substitute IA as 5 ampere and torque as 20 ampere. If you substitute, you'll get the value 545. In the same way, for the next set of reading, you have to substitute IA as 10 ampere and T as 50 Newton meter. So in this way, you'll get the value 434. Like this, you have to keep on substituting the value, then you'll get the value. Now you have the armature current value, and also you have the speed for the corresponding armature current value. Then you can easily plot the graph. So what is speed current, armature current characteristic? Here, x-axis, we are going to take the armature current, and in the y-axis, we are going to take a speed. Hence, we have deduced, or we have written the graph. In this way, we have to plot. Okay. So next, the second problem. The following figures give the magnetization curve of a DC series motor when it is working as a separately excited generator at 600 RPM. That is, they have told you that the magnetization curve of a DC series motor, that means it is a curve between field current and the EMF generated. When it was running as a separately excited generator, its speed was 600 RPM, and the total resistance of motor is again 0.8 ohm. We have to draw again the speed torque curve when it is operating at a constant voltage of 600 volts. So next, let us list out the data. The supply voltage, again here it is 600 volt, and the motor resistance is nothing but armature resistance plus series resistance. resistance, which is nothing but 0.8 ohm, and again it is equals to the and it is again same as the armature resistance, which is nothing but 0.8 ohm. And here the first speed we are taking as 600 rpm. What is the speed? It is the speed of the motor when it is operating as a separately excited generator. So next, let us draw the table, and let us see here the field current in ampere. We know that it is 20, 40, 60, 80. And the back EMF also they have given, which is nothing but E1 when it was running as a generator. So that also we have here. Next, we have to calculate the back EMF. So again, why we have to calculate back EMF? Because in the formula of the speed, we have this value. So back EMF is nothing but what? V minus Ia into Rm, correct? Next, again, what is V? V is nothing but 600 volts, correct? So you can see here, V is nothing but 600 volts. Then IA is nothing but 20 ampere, because in the series motor, field current is same as the armature current. Hence, it is again 20, and motor resistance is 0.8 ohm. So therefore, V minus IA RA, that is 600 minus 20 into 0.8, which is nothing but 584. Again, for the next set of reading, the voltage V is 600 again, and armature current is 40, and motor resistance is 0.8 ohm. So substitute, and you'll get the value, which is nothing but 568 volts. So in this way, we have calculated the back EMF. Next, let us calculate the speed. So speed is speed in RPM when it is running as a motor. So, so what we can write here, it is actually the this relationship, that is speed and that is this relationship, that is N1 by E1, it is nothing, N1 by E1 is into V minus IA into Rm. We have already calculated V minus IA Rm, and N1 is nothing but 600 RPM, you can see here, and E1, correct, and E1 is nothing but 215. That is for each value you have to keep on changing the E1 value, and also V minus IARM value. Hence, you will get the value 1630. In this way, you have to draw. And the torque formula we have, this is the formula for the torque calculation. And again, substitute all the value. V minus IARA is again keeps changing, and the speed N is nothing but this value, and IA is nothing but 20. So like this, you have to substitute, and you will get the value. And we have drawn the curve, and you can see here speed and torque is inversely proportional. By this value also, you can see here it is inversely proportional. When speed is high, torque is low, and again when speed is low, torque will be high. Like this, we have to draw the graph. Next, let us move on to the third problem. A DC series motor drives a load. The torque of the motor varies as square of speed, and the motor takes a current of 15 ampere. When speed is 640 rpm, calculate the motor speed and the current drawn when field winding is shunted by a diverter of same resistance as that of the field winding. Neglect all motor losses and assume that magnetic circuit is unsaturated. So that means what? Here they are going to use again the DC series motor. The motor is coupled to a load here. That means the motor is driving a load, and the torque of the motor is varies as a square of speed. So here they have given the relationship that the torque is not only inversely proportional to the torque is here the torque and speed relationship, they have told that is torque is directly proportional to the square of speed, that is T is proportional to N square. They have told you here. And the motor takes a current of 15 ampere, so which is a armature current, and the speed is 640 rpm. We have to calculate what is actually the motor speed and the current drawn. We have to calculate, please remember, it is the here we have to calculate the motor speed and the current drawn when field winding is shunted by a diverter. That is, we are going to connect again we are going to connect another winding of same resistance as the field winding across the field winding. Hence, we have the two windings are in parallel now. Next, neglect all the motor losses and assume magnetic circuit is unsaturated. Okay, so here flux is not constant. So that is the condition. Solution, let N1 be 640 rpm, and the series current is same as armature current, which is nothing but 15 ampere. and let speed be N2 and line current be I2 when field winding is shunted by a diverter of same resistance as that of field winding. Before it was speed was 640 rpm and current was 15 ampere. Now if I connect another winding of same resistance across the field winding, then what would be the speed rpm and what would be the current that we have to calculate here. So series field current is usually half of the I2, because if the two resistors are in parallel and the equal current will be distributed among the two windings, correct? So same that is the same current, or the half of the current will be distributed to the two windings. So hence we can write the relationship as ISC2 will be equals to half of I2. Next, because line current I2 divides equally between series field and the diverter, because both are in parallel and of same resistance. Being equal values, IA is equals to I. Next, since torque developed is proportional to IA, phi into IA, we know that torque is proportional to flux into armature current, and we can write it as flux into the common current I. And so by this relationship, it is a direct relationship, correct? So if it is a direct relationship, then how can we write T2 is proportional to phi to I2, because it is a direct relationship, and T1 is proportional to phi 1 I1. If I remove the proportionality constant, then I can actually write the equal sign. Therefore T2 by T1 will be equals to phi 2 I2 divided by phi 1 I1. Phi flux is constant over here, hence let us cancel these this flux value, and again I2 is nothing but what, half of I2. And also they have told that torque varies as square of the torque varies as here they have given the condition that torque of a motor varies as square of speed, and as it is square of speed, we can write in this way, that is half I2 square. And also we know that flux is directly proportional to the current. Hence, in the place of flux also, we can write the current value. So remember why we have written here, torque is proportional to phi into Ia, and instead of Ia, I can write as I only. Hence, we have write this equation as it is directly relationship. Hence, we have written T2 is equals to phi to I2, and T1 that is T2 by T1 is equals to phi to I2 divided by phi 1 I1. If it is inverse relationship, then we would have written T2 by T1 will be equals to phi 1 I1 by phi 2 I2. As it is direct relationship, we have written in this way. And we also know that flux is proportional to the current, correct? Flux is proportional to the armature current. Hence, instead of phi, we can also write I2, correct? Phi 2 will be equals to I2, hence we have written I2 again, and phi 1 is also equals to I1, hence we have written. And we know that this current is half of the half because ISC2, you can see here, it is half of the I2, and here I1 will be equals to I1 again. Here it is as we are connected the another winding across the series connection, hence it will become half of I2 square. Okay, hence we have written in this way. Because phi is proportional to ISC and magnetic circuit is unsaturated. Or T2 by T1 will be equals to I2 square divided by 2 I1 square. Let this be equation 1. Also, T2 by T1 is equals to N2 square divided by N1 square, because in the problem they have mentioned that torque is proportional to the square of speed. Hence, we have written in this way. That is, as it is a direct relationship, T2 by T1 will be equals to N2 square by N1 square. So now let us equate these two equations. When we equate these two equations, then we will get this relationship, that is N2 square by N1 square will be equals to I2 square divided by I1 square. So next, let us transfer. Let us do the square root on both sides. So if we do the square root on both sides, then the square terms will get cancelled. Then we will get N2 by N1 will be equals to 1 by root 2 into I2 by I1. Then neglecting the voltage drop in armature and the series field and assuming applied voltage is constant, then we can actually write write n is proportional to 1 by 5, because we got to know that n is proportional to V minus IARA by 5. IARA's drop is very small with respect to voltage, so therefore we have neglected that term. And here we are assuming that applied voltage is constant, hence speed is inversely proportional to flux. Or again, flux is proportional to the current, hence we can write in this way, that is N2 by I1, N2 by N1 is equals to 1 by root 2 into I2 by I1. Let this be equation 3. Next, let us equate these two equations. So N2 by N1 is equals to phi 1 by phi 2, because it is inverse relationship, hence we have written in this way, that is phi 1 N2 by N1 is equals to phi 1 by phi 2, whereas phi 1 is nothing but I1 and phi 2 is nothing but 1 by 2 times I2, hence this will become 2I2 by 2I1 by I2. Next, let us compare these three equations, 3 and 4. Hence, we will get the value, that is 1 by root 2 into I2 by I1 will be equals to 2I2 by 2I1 by I2. Hence, we can write it as current drawn I2 is nothing but, I2 we want here, right? I2 is nothing but square root of 2 into root 2 I1 square. And we know that the current I1, that is the armature current or the initial current drawn, will be 15. Hence, we will get the value 25.227 ampere. So, this is the current I2 one. Another winding is connected across the, connected across the field winding, that is series field winding. Next, speed we want. Speed is nothing but again 2I1 by I2 into N1 by the above equation. Hence, again I1 is 15 and I2 is 25.227. Hence, we will get the value 761 RPM. So, this is the speed and current when we connect another field winding of same resistance across the motor. So, hence this is the value. Hence, we have calculated the speed and current. So, this completes the problems with respect to the operating characteristics of DC series motor. So, in the next class, we will study is DC series motor is suitable for the traction system, or DC traction motor is suitable for the traction system in detail. Thanks for watching the video.